Chapter 2, Part 2. Now we're going to look at the atmospheric response to solar radiation, what happens to solar radiation when it interacts with the planet, also the planetary energy budget, which is simply a balance between incoming solar radiation to the planet versus outgoing long-wave radiation leaving the planet. As a recall from last recording, there is an angular dependence on how much solar intensity you get at any point in the planet, only where the solar radiation is coming in perpendicular to the surface of the planet where you get a maximum. Anywhere else where it's coming in at an angle, that radiation gets spread over a greater area and therefore your intensity goes down. The upper left graph here shows this dependence using the annual average top of atmosphere solar radiation. That is, the amount of radiation incident at the top of the atmosphere before it interacts with any gases, clouds, or the surface. So you see it's just a geometric relationship where the tropics, where the sun's directly overhead a lot of the year, get the most incoming solar radiation, and it decreases as you go to the poles. The annual average solar radiation that actually arrives at the surface is something altogether different, because now you have to look at how many clouds are around each region, able to reflect or scatter away solar radiation before it reaches the surface. For instance, we see the Sahara Desert here with a really strong amount of solar radiation arriving at the surface, and that's simply because it's cloud-free. Other places with frequent clouds like the Amazon Basin or the Congo Basin won't have as much solar radiation able to arrive at the surface. The difference between these plots is atmospheric absorption and reflection again. In other words, clouds or gases that don't let the solar radiation transmit to the surface in the lower graph. There are a variety of interactions that can happen with light and the surface or with clouds or gases in the atmosphere. The first I'll point out is scattering. As light comes in, it might get scattered by a cloud particle, it might get scattered by gases, and it could get scattered in all directions, or sometimes there's preferential directions depending on the size and nature of the scatterer. There could be reflection, which scientists typically think as a specific type of scattering, where instead of being scattered in multiple directions, that which is scattered in a singular direction or reflected in a single direction. Next is absorption, which is shown here in purple, which means that molecules or gases or even the surface could absorb solar radiation. That which absorbs also emits, so the surface or the gases or anything with a temperature above absolute zero can emit radiation. And we looked at the Boltzmann and Wien's law in defining how that radiation gets emitted. Also, there's transmission. If light is not scattered, reflected, or absorbed, it is transmitted through the atmosphere, which simply means it passes through unimpeded. Lastly, shown here is refraction, which is a bending of light, which typically happens between different mediums, for example, between air and water. Now, the albedo is the fraction of the incident radiation that is reflected or scattered. And here we're showing a low albedo, or shown as an albedo of 0, all incident light upon it gets absorbed, which means none is reflected. So the albedo, again, is the fraction that is reflected, none of it's reflected, so the albedo is 0 in this case. The next case, we're showing an albedo of 0.5, which means 50% of the light incident on it gets reflected away, which leaves the other 50% to be absorbed. Lastly, we can consider a very high albedo object, say an albedo of 1, which means that all light incident upon it gets reflected away, leaving none to be absorbed. Typically, we relate albedo to visible wavelengths, but one can consider frequency-specific albedo values as well. For example, what is the albedo with respect to infrared radiation and things like that. Now, the albedo of the moon is about 0.07, meaning 7% of light incident upon it gets reflected, but Earth's albedo is much higher at 0.3. 30% of light incident upon the Earth's system gets reflected back out. Now, this picture shows the moon is pretty bright, and that's because it's contrasted against a very dark background. What's the big difference between Earth and moon's albedo? Well, really, it's clouds. Earth has a lot of condensed clouds here, which make up a great proportion of that average albedo of 0.3 for the Earth. Here's the albedo of different things expressed in percent instead of fraction. The first thing we can see is that fresh snow has a very high albedo, sometimes as high as 95% or 0.95. Clouds, the lower the cloud, typically the thicker the cloud and the more bright, so cumulus clouds near the surface have relatively high albedos of 0.8 or so. Stratus clouds, there's a variety of stratus clouds, but in general we can consider most of them in the mid layers, about 0.7 of an albedo, and then cirrostratus clouds, which just means stratus clouds higher in the atmosphere, less water vapor to work with, thinner clouds, they can have albedos of 0.5 or so. We can also see that water and vegetation are not very reflective, meaning they have very low albedos. Here we're looking at different vegetation here, somewhere in the range of about 0.15 to 0.2. Of course, they don't want to have a high albedo because they want to absorb a lot of sunlight for photosynthesis. Now, water has an extremely low albedo at most angles of incident sunlight. Only when sunlight comes in at an extreme angle, at extreme sunset, during sunrise, will you have high reflectivity. However, when the sun's at more normal angles coming in to the water surface, it absorbs almost all of it. And so the reflectivity is very low for water. Here's just an illustration showing that ice tends to reflect solar radiation, which you can really see as white. Again, this means it's reflecting all the colors towards your eye. And then water tends to absorb solar radiation, appearing as black here because it's not reflecting so much radiation to your eye. Large particles, such as cloud particles, tend to scatter all wavelengths more or less equally. Scattering gets a lot more complex than I'm illustrating here. White light tends to be scattered off these large cloud droplets in all directions. White light gets multiple scattered as it goes through a thick cloud, leaving only so much light to escape the bottom, which is why cloud bases are typically dark. Small scatterers, such as molecular oxygen or molecular nitrogen, preferentially scatter shorter wavelength light, blues and violets. This is what's called Rayleigh scattering. Now it turns out that Rayleigh scattering, if you're going to quantify it, is proportional to 1 over the wavelength to the 4th power. And that's just to say that it's a strong function of wavelength. So the smaller the wavelength becomes, the bigger 1 over wavelength to the 4th power becomes, and the more Rayleigh scattering will scatter the shorter wavelengths towards your eye. Transmissivity, the proportion of solar radiation passing unimpeded all the way through the atmosphere, depends on 2 things. First, what's in the atmosphere? Is there clouds? Is there dust? Are there other kinds of molecules that's going to absorb that solar beam? Also, it depends on the path length. Here we're showing a short path length as the radiation comes in perpendicular to the surface. It only has to pass through so much of a path of the atmosphere. But if it comes in at an angle, it's passing through a much greater path length of the atmosphere. Therefore, there's more time for other objects to scatter it away and not let it transmit through the atmosphere. So the sky is blue again because of Rayleigh scattering. Those small molecules preferentially scatter the blues and the violets towards your eye. So why is the sun reddish at sunset? Well, that which is not scattered away towards people looking at the sky in all directions, in other words, the part that transmits away and does not get scattered, takes out the blues out of the solar beam, leaving the more reds in there. So if you're looking at a sun that's going down the horizon, there's a long path length. There's a lot of molecules in the way to scatter away the blues and the violets, leaving red to be transmitted towards your eye. So why are the clouds also reddish at sunset? Because they're simply reflecting that red beam towards your eye as well. Now, absorption is critically different than scattering or reflection because this retains, the object that absorbs retains the incident radiation and converts it to another form of energy, either potential or kinetic energy. Typically, we think of an increase of heat of molecular absorption, for example. Different gases absorb different wavelength. Ozone and oxygen are pretty good UV absorbers, but greenhouse gases like carbon dioxide, methane, water vapor, and more absorb infrared radiation, long-wave radiation, but not short-wave radiation like solar radiation. Not many gases absorb terribly well in the visible range, where lots of solar radiation is, thus much of the solar beam makes it to the surface. Again, emission, everything with a temperature above absolute zero emits radiation. That includes everything in the entire climate system. What type and how much of radiation they emit is strongly tied to their temperature. Again, we're just looking at the Boltzmann law here that says that. Everything emits, and you can quantify the emission based on their temperature. Radiation from things with sunlight temperatures tend to have shortwave radiation as their maximum wavelength of emission, and that's defined by Wien's law. Radiation from things with Earth-like temperatures, pretty much everything in our climate system, emits infrared radiation based on its temperature. These 2 charts are looking at outgoing long-wave radiation from the Earth's system. Where's most of the radiation coming from? Well, it's not as you'd suspect because where you think it's hottest at the equator, you're not seeing as much radiation coming out into space as from, say, the subtropical bands. And this is because of clouds overlying these areas. Clouds are overlying the Amazon basin in January, over the Congo basin, and over Indonesia. Those clouds are relatively cold, so due to the Boltzmann law, they're not emitting as much radiation as to space, which is being measured here. Instead, a lot of Earth's radiation is escaping from the subtropics, which are relatively hot but also relatively dry with little clouds. Therefore, that hot surface has a better chance of emitting a lot of its radiation towards space. This graph considers radiation budgets at different layers in the climate system. First, we'll look at the top of the atmosphere, where the budget is balanced. 100 shortwave units of energy coming in, 30 units of those are reflected away by the atmosphere and the surface, leaving in a planetary albedo of 30 over 100 or 0.3. The other 70 units are lost by long-wave radiation out to space. In the atmosphere itself, we have shortwave absorption of 25 units, long-wave radiation losses of 54 units, leaving us a net radiation deficit of 29 units. At the surface, we have shortwave absorption of 45 units, long-wave losses of 16 units, leaving us with a net radiation surplus of 29 units. In order to balance this budget between the surface and the atmosphere, there's other heat transfer processes at work. This chart looks at the planetary energy budget. There's 100 units of solar radiation coming into the climate system. Of that, 20 units are absorbed by the atmosphere, and another 30 units are reflected and scattered back to space by the atmosphere and the surface. This leaves 50 units that get absorbed by Earth's surface. Now, Earth's surface can radiate some long-wave radiation directly to space, but not a whole lot gets radiated directly to space because there's greenhouse gases and clouds in our atmospheres that will intercept it. So Earth's surface will actually emit 107 units of long-wave radiation to the atmosphere, which absorbs it. It can also give heat to the atmosphere by latent heat exchange. That means simple evaporation cools the Earth, the water vapor rises up, condenses in the clouds, adding heat to the atmosphere, which is a vertical transport of latent heat. Or thermals, convection, can have warm air rise directly, giving heat to the atmosphere as well. When you look at the atmospheric budget, it ultimately gives off more long-wave radiation directly to space than Earth's surface does. In other words, the atmosphere absorbs a lot of infrared radiation from the surface, and it's up to the atmosphere to ultimately radiate that away to space to cool the climate system. At the same time, the atmosphere emits 96 units of long-wave radiation back to the surface. The difference here between long-wave Earth radiation coming from the surface, getting absorbed and then emitted back by the atmosphere back to the surface, this is really the greenhouse effect. And that's a function of how many greenhouse gases we have in our atmosphere and also how many clouds which can also absorb and re-emit infrared radiation. Specific greenhouse gases absorb specific wavelengths of infrared radiation. This chart shows this effect by looking at CO2 and water vapor, and this crosshatching means that they effectively absorb about 100% of IR radiation from about 12 micrometers to 25 micrometers in wavelengths. There's also absorption bands for CO2 and water vapor at shorter infrared wavelengths in, say, the 5 to 8 micrometer wavelengths, and also water vapor is effective in about the 2 to 3 micrometer wavelengths as well. Ozone in the troposphere is a greenhouse gas too that doesn't absorb 100% at specific wavelengths, but more like 75% of wavelengths somewhere in the 10 micrometer regime. This hole here means that we do not have greenhouse gases that absorb at these wavelengths. So these are the wavelengths that could be emitted from the surface and make it through a clear atmosphere because there's no greenhouse gases to absorb them. This is called the atmospheric window. As a whole, Earth cools by the sky and clouds radiating away energy to space, not by the surface radiating directly to space. Heat is moved from the surface to the sky by radiation, radiative transfer, but also by thermals and by water vapor transport. This energy, once in the atmosphere, can now be radiated to space directly in order to balance that incoming solar radiation at the top of the atmosphere. To get a simple understanding of the planetary budget of radiation, that which comes in from the sun versus that which leaves the Earth, We can do a simple example here. Which of these two black bodies would cast a larger shadow if both have the same diameter? Here we have a flat disk perpendicular to light coming in, and here we have a sphere intercepting the light. Since they both have the same diameter, they both intercept the same total amount of radiation, which means they cast the same shadow. Of course, this one will be more complicated because the radiation is coming in at different angles. However, we can make use of this simple physics to simplify a planetary energy balance problem. Here we see the sun's radiation, the solar constant, coming in perpendicular to the Earth at one point. However, we just showed we could substitute this complex sphere with a flat perpendicular disk taking in that solar radiation. So if you consider the area of that disk as pi r squared times the solar constant, that's how much radiation is coming in to the surface of that disk. Of course, you have to multiply times the albedo, the effective albedo, 0.3 of the Earth, to show which part gets reflected away and which part actually gets absorbed. So if you combine these two equations, pi r squared times s minus pi r squared times s times a, you come up with how much incoming solar radiation gets absorbed, which is the solar constant times the area of that perpendicular disk times 1 minus a, that fraction that's absorbed. What's outgoing, since anything with a temperature above absolute zero, which is anything on the surface of the Earth, is emitting infrared radiation back to space all the time, you have to consider the entire surface area of a sphere, which is 4 pi r squared, times the Boltzmann law, which is sigma t to the fourth. So we can strike a balance here with incoming radiation absorbed on the right here, pi r squared s times 1 minus a, versus what's emitted, the whole surface area of a sphere, 4 pi r squared, times how much gets emitted per square meter, which is the Boltzmann equation, sigma t to the fourth power. If you balance these two equations, incoming solar that's absorbed versus outgoing long-wave radiation emitted, you come up with this equation in the upper right. And you'll soon find that pi r squared falls out of this. If you then solve for the effective radiating temperature, you get the effective radiating temperature equals the fourth root of S times 1 minus A over 4 times the Boltzmann constant. Now the effective radiating temperature is strictly what the temperature would be if we were a black body, if our planet was a black body with no atmosphere whatsoever. This equation does not give you any idea of the surface temperature, which includes effects from greenhouse gases. Instead, it considers what would the temperature be if we did not have an atmosphere and if we were a perfect black body. If we recall that S for any planet can simply be found using the inverse square law and considering the distance from the sun, you can use this equation to find the effective radiating temperature of any planet in the solar system. You will get practice with this equation in homework 1. Key points from Chapter 2, this section: how much solar radiation ultimately reaches the surface depends on the state of the atmosphere and the path length of the solar beam. The percent of incident solar radiation that actually gets absorbed at the surface also depends on the reflectivity of that surface. Once solar radiation is absorbed at the surface, it gets converted to heat for the most part, and much is re-emitted as long-wave radiation. Some of the solar radiation evaporates water, allowing for latent heat release in locations where this water condenses in the atmosphere. Some of the solar radiation warms surface air, which is transported to the upper atmosphere by weather systems and convection. 7% of the long-wave radiation that leaves Earth's surface makes it to space directly, and this is because we have this atmospheric window where we have certain wavelengths of IR radiation that aren't absorbed by Earth's greenhouse gases. Much of IR radiation absorbed by clouds and gases, and these emit long-wave radiation in all directions. Much of that long-wave radiation comes back to the surface, in other words, the greenhouse effect, and some of it radiates to space, which ultimately is the real thing that cools the atmosphere and the climate system as a total.